Alrighty, we'll start slow, and anybody that comes in late can have a chance to catch up. So my talks are pretty relaxed and informal, especially in a room this size. So if there are any questions or anything that comes up that you're unclear on, or just have a question you want to pop, just shoot your hand up, and we'll take it and just see how it goes from there. So don't be inhibited in asking or anything. Alrighty, well that's who I am. There's the Twitter handle for the language that I'm developing, and the GitHub repo organization. Actually, there's several repos in there for this language. So what is this language? It's called Takada, and it's inspired by Clojure because S expressions are the one true syntax. I freely admit that I am a bigot in that respect. All other syntaxes are inferior, and S expressions are just the way to go. I picked up Clojure right when Rich went public with it, within like a couple of months after Rich posted the stuff. So I'm a longtime Clojure programmer. Before that, I did embedded software for firmware and Linux kernel drivers and stuff. And so I loved Clojure. I absolutely loved it. Especially the little bit of syntax that Rich added to it was just great. And the immutable data structures, once I got my head around them, were awesome. But it was on the JVM. And that just grated on my nerves for the past 10 years. So I started to implement a Clojure that would compile to C. And that was the original reason to do Takada. But as I kept doing it, I kept tweaking things. And finally I was like, okay, fine. This is a language inspired by Clojure. That is a Lisp that's ported to C, or that compiles to C. It runs just about anywhere that C you can compile C on. It doesn't do anything esoteric. And so as a whim one day, I just ran it through the WebAssembly toolchain, and all the regression tests passed. I was shocked, except for the multi-threaded. I have some futures and stuff, and of course WebAssembly doesn't run on a multi-threaded environment yet, but they're working on it. And so those failed, but everything else just worked. So I was like super psyched. And the compiler is written in itself. It is self-hosting at this point. It's about under 5,000 lines of code for the actual code generation. The parser, the AST definition and stuff, those are in libraries, and that's adds lines to it. The idea being that anybody that wants to write tooling for Takada can use the same libraries that I use to build the compiler. I want as little to be off limits to the normal Takada programmer as possible, including the compiler. I mean, it's kind of a mess because it grew organically, but I hope to clean it up and make it understandable, even the compiler itself, to a run-of-the-mill normal Clojure or Takada programmer, so that it kind of loses the mystique. I'd never written a compiler before I did this, and it's been a fascinating learning experience, and I want to share that. I want people to be doing this kind of stuff. It's a pain in the butt, but it's not like beyond the capabilities of most programmers. So, alrighty, let's dive into the meat of things. Ooh, scary diagram. Not really. This is a call tree. I don't know if anybody familiar with that term, call tree, or is something I just made up. Okay. So this is kind of the structure that's going to illustrate a lot of the points in the first half or so of the talk. And so I'm going to spend a little bit of time explaining what this is and what these different things mean. So let us begin. This is the main line of a very simple Takada program. One expression that prints the word 10. That tick is a symbol literal, and increments the number 9. So it's going to print 10 as a word and then 10 as digits, 1, 0, and put a character return at the end. Very simple looking little program. So and main is the main entry point of a Takada program. That's where the execution begins. So the first thing main does is call inc. That was the inner expression. So inc gets called, and it gets passed a 9. In this case, that's x. So then inc in turn calls plus, and it passes it 2 numbers. Plus in turn calls add numbers. Now add numbers is a leaf in the call tree. It has a chunk, as you can see there, a chunk of C code that when the compiler sees that, it just drops that chunk of C text right into the generated text. So then add numbers executes that little bit of C and returns the value back to plus, which returns it back to inc, which returns it back to main. And then main then calls println. Println's a little bit more complicated, but the innermost expression is that call to interpose. Interpose, then, the innermost expression there is a call to seek. Now seek is kind of what's called a type class. It is a function definition that is dispatched on the type of the first argument. Yeah, I think in Haskell, a type class can be dispatched on the types of all the arguments. But in Takada, it's only the first argument. In Clojure, this is called a protocol. So this is a type class. So seek, interpose doesn't know which seek he's calling because that is determined by the type of the value that was passed into interpose. But he just calls seek. The compiler codes up a dispatch chunk of code that takes the type, finds the implementation to execute, and then executes it. Returns the value back to, back to interpose. And then interpose calls Flatmap, which is itself another one of those protocol functions or type classes. Except in this case, Flatmap is also given a function, and in this case an anonymous one, that gets executed. We don't know how Flatmap calls this function. We just know that it does. And that anonymous function calls list, which is a leaf function, and that just creates a list out of the arguments that it's passed. If I'm going too fast, yes?
Did you say what seek does?
No, I didn't. Okay. What it does is returns a list. But yeah, I'll get to that here in just a second. So yeah, list, then returns its results back to Flatmap, which goes back up to interpose, which then calls rest, which is another one of those protocol functions. Does whatever it's going to do, then passes that result back to interpose, which goes back to println, which then calls Flatmap again. And again, we don't know what it does, but it's going to do something. That invocation of Flatmap got past string list, which is itself a protocol function. So string list does its work, passes back to Flatmap, back to println, and then println calls map, and then map in turn calls PR star, which is another leaf node, and that's what the circle the double border means. It's a leaf. PR star back to map, back to println, back to main. And then your program's over. So this, you do a depth first traversal of this tree, shows you what functions are going to be called as this little thing executes. So everybody with me, that was a pretty quick run through. You guys are brilliant. Awesome. When I do it is. And this is more of just a conceptual tool to be used. I have some ideas on to make an actual tool to do this with some interesting things, but right now it's just a conceptual thing. All right, let's look at add numbers in a little more detail. Here's where the fun begins. So this inline C expression that forms the body of add numbers. You'll see that it says inline C integer. So that says that this little snippet of C code is always going to return an integer value. And this is a Takada integer, which is a boxed C integer. And it's always 64 bits. So this is not returning an int or an int64 or whatever. It's returning an integer value in Takada. So let's take out that little snippet of C, because C is just ugly. Okay, so these are some assertions, some runtime assertions that get dropped in, because add numbers can only work on integers. They can't, if you pass it a string, it's going to blow up. Or actually, if you pass it a string, it's going to give you a bad, it's going to think it's an integer and give you a bad result coming back. So we put some runtime assertions in here. And you'll see there's the box is now a box instead of a ellipse. And it has a little dot on top of it. So what that box means in my scheme of things is that the contract for this function is totally specified. It is no longer just, you no longer have to guess what this function takes as parameters or what you're going to get back as a result. So that's what the square means. The dot means that the runtime assertions are at the, as you come into that function. It's like a contract, precondition. Geez. Sometimes when you're giving talks, you just space on certain words. So that's a precondition. Okay, but the compiler is smarter than your average bear. And so it sees these runtime assertions on the parameters being passed into add numbers, and it remembers that. So instead of dropping those assertions, compiling code to be executed at runtime into the call to add numbers, the compiler just remembers that. And when it compiles the call site in plus, that's where it goes to drop the runtime assertions. But now, we know the contract for plus. We know what it needs as parameters coming in because we can just promote those assertions up the call tree. This is type inference, where you take typing information from one part of your program, the compiler does, and uses it to infer type information for another part, where you don't have to actually specify, the programmer doesn't have to specify it. So you put as much work on the compiler as possible. These runtime assertions can be anything, and we'll see some examples later on. Right now, I have a handful, like 3 or 4, which does an amazing amount of work in verifying that your program is correct. A Takada program is correct. Catches all kinds of bugs. But it's only like 3. You can have anything in here, and I have ideas of what to add at these runtime assertions, including the possibility of having one be a predicate function, which has some implications for later. So, any questions? Everybody tracking?
Predicate from the user? Predicate sent in by the user?
The programmer can put an assertion.
Okay, I get you.
Oh, yep, right. Next slide, or not next slide. Okay, so now we know about plus. So then if we go up the call tree to inc, these assertions are being promoted up. But at this point, at this call site, the compiler sees that the assertion for the first argument is always going to be satisfied by this literal 1. And so it just says, okay, fine, I don't have to worry about this anymore. And so it drops that assertion out. And it will never be done at runtime because you're guaranteed statically that it's always going to be satisfied. And so now we know the contract for inc. It's always going to take an integer and return an integer. And then we promote that back up to the main. But here, inc is being called with the literal number again. And so that goes away. So throughout this entire chain, we've taken these assertions from the add numbers, the leaf, promoted them up, and then determined statically that they're always going to pass. And so they go away. Now let's look at interpose. Things get a little more interesting. Here's interpose by itself. Okay, so seekable, seek, is part of the seekable protocol. And every data type in Takada, you don't have to implement these protocol functions. But if you're going to pass it into Interpose, you need to, because Interpose is going to call seek with it, and seek is going to call this, and if there's not a implementation for it, then you're hosed. But, so we don't know what seek is going to get given as a parameter. That's what that COLL is. But we know that whatever it does, that implementation has to return a list. That's what this assert result is. So whatever seek does, whatever data type seek does, it's going to return a list.
Where does it come from?
Where's what?
Where does it come from?
It's just a free variable. Its scope is limited to the assert result expression. And it could be literally anything. Okay. What? Not that I know of.
It's a special form, right?
So yes.
Assert result is a special form.
Assert and assert result are special forms. But they look like normal things. And the expression inside, like the instance question, there's an actual function in the Takada core library that will see if you execute it, it will see if Z is an instance of list. But the compiler, when it compiles the assert result, it sees that that's an instant call and does it statically rather than actually make a call to the core library function. Okay, so once you return a list out of seek, once you know that that is coming out, then everything else becomes concrete. The compiler can determine what these, like what Flatmap. It's always going to be calling the Flatmap for the list. And then that the code for that Flatmap is right here in the middle. It calls list concat and list map, which are concrete functions. And so you know the contract then at compile time for the rest of the call tree for Interpose. And so these dispatches don't have to happen at runtime. The compiler hard codes those in because he knows that seek is always going to give a list. So that's a huge optimization that you can get away, you can eliminate a lot of work by just having that little bit of information. Everybody good? Alrighty. This is just a little slide that kind of shows what Interpose does. I think you guys are smart enough to know, so we'll skip it. So then you carry that throughout the rest of your call tree. This is what it looks like. Pretty much everything gets specified by just a little snippet of static information, except for that call to string list. That's still hanging out there. And there really is no way because that's the items that's in the list. And so that's hidden from the compiler. He doesn't know what items are going to be in the list. But everything else is pretty much fixed. And so it just gets compiled and it just burns through the stuff. So that's the magic of static typing. Really is a good performance hit. So one of the things with, like I said with Takada, is I wanted to give as many of the benefits of static typing to programmers that are not familiar with or see the benefit of it with as little cost as possible. Because static typing is great, but there is a cost to it. And if you don't see the benefit, then you don't want to pay the cost. And so Takada, the idea is to give that benefit to as many people as possible. And then, if as you're debugging your code or whatever, you actually get a bug that could be solved by asserting something, then you can just drop an assertion into your code at some place, and then that bug gets caught at compile time. So you can add as much typing information as possible, or as you want, and as you see value for.
Do the assertions use sugar to purely compile time expressions, or are they at runtime?
That's the next point.
Right. I mean, my related question is there a dynamic fallback?
That's the next point. All righty. So let's look at this little thing. A little main function. Frob and nits are two functions I made up. And there's that call to inc in the middle. So main calls nits, doesn't know what nits does, doesn't know what nits returns. It returns something. Then calls inc with the result of nits. And inc does what we've looked at it doing. And then takes the integer that comes from inc and calls frob with it. But you see that the little dot on top of inc. So that is where a runtime check gets dropped in. So we don't know what's coming from nits. So we have to put a little check right there that says, at dynamic runtime, as when that call site gets run, it says, is this thing an integer? If not, it crashes. So in Takada, there are a couple of things that are unique about it. There's no null value, there's no booleans, and there is no exceptions. If something breaks, it crashes. But most everything should be able to be caught statically. So once your program compiles, the only things that should crash it are, with one exception, which I'll cover in a second, are things that are like outside the control of the programmer. That one exception is if you call a protocol function that type is not implemented. I have an idea of how to catch those, but it's going to require more work than what I'm willing to put into it, that feature right now. So that's kind of a bad deal. But all things in their due time. So does that answer the questions about the dynamic check and stuff? Yeah.
Why are there no booleans? Okay,
I did not explain that. That's a longer explanation that I'll be glad to talk to you about afterwards.
Okay.
So one of these days I'm going to come to LambdaConf and give a talk on just Takada. Actually, I've already done 2 that way. 3 years ago, I gave a talk on the next great programming language. That was a follow-up to John DeGoza's talk the previous year. And then last year, I gave another talk. But this is just about the type system. OK, so I used to call this gradual typing. This is not gradual typing. Came to LambdaConf, talked to Jeremy Seek, and he goes, no, that's not gradual typing. That's something called soft typing. But I decided to leave the slide in here so that, as an example of, you do not have to know everything about your talk before you submit it or before you give it. Just giving a talk is a great way to learn things. So, submit your talks, figure out what you need to know to give the talk, and then go for it. This is soft typing, and I looked it up, did a quick Google search, and read spent about 30 seconds reading the whatever page that popped up, and it's like, yep, that's it. It just drops a runtime check at runtime, for runtime, at the point where the compiler cannot determine that a constraint is going to be satisfied. But it's as high up the call tree as possible, so that if there are redundant ones that come from lower down, they get combined into a single check. And you know that below that check, everything is fixed, and you can erase the types and the code just runs. Okay.
I got a question.
Yes. I'm with you.
So with Clojure has a warning for warning on reflection, that sort of thing. Would there be benefit there in having a warning on can't figure out this type? I'm going to have to add a runtime check there.
So one of the ideas, one of the things I want in Takada is to make tooling for Takada. Anybody can make tooling for Takada.
Okay.
one of the tools I have an idea for is to draw these call trees. It ingests a Takada program, spits out this massive graph of things, and it puts a red box wherever you have a possible runtime. And then it's like a web page, and the program would click on that box, go to the source code, and put an assertion there. That's the dream. If anybody wants to take that up, talk to me. I will do my best to support you in that endeavor. Okay, let's look at this function, FrogNets. Anybody know where FrogNets comes from? Well, I don't know either, but I think it comes from the game Zork, which I played in my misspent youth on an Apple II Plus. Okay, so FrogNets takes two values, two parameters. And so we have some assertions on these parameters. The first assertion is that x is always going to be less than 4, and that L is always going to be a list, and that the length of L is always going to be greater than 4, and that FrogNets is always going to return a vector. These kinds of assertions where there are additional constraints on the parameters in addition to just their type. It actually depends on the type, the value, rather than just the type. This is dependent types, or dependent type checking. So that you can add new information or more information than just say it's a type of a list. And you can restrict the set of possible values that are passed in. And the compiler can check if these constraints are satisfied at runtime, just like doing a type check. And it can drop a runtime check in, for dynamic checking. It's the same mechanism. In the compiler, there's a little interface that you want to build a constraint, you just implement this interface. All the plumbing, all the mechanism is there to take that and do the right stuff with it. Now, implementing that interface is a little bit tricky, but regardless.
What's the return type of one of those constraints?
There is no return type.
Okay.
Because these are special forms, and they get inside the assertion, and they get done at runtime, or at compile time. So there is no, I take that back.
Because it's written in, it's also in Takada, right?
Yes. So these expressions in here, if they were as functions, because like less than, that is a literal function, it would return a maybe value.
Maybe whatever the value of x is.
So yeah, it would. So in the case of a less than, it would return a maybe. If x is less than 4, it would return maybe whatever x is. If it was not, there's a special maybe value called nothing, which is empty, which satisfies. So for an assertion, the conceptual idea is that the inner expression gets evaluated, and if it returns a maybe, then the assertion passes, and if it returns a nothing, the assertion fails. Thank you for pointing that out. So, dependent types. This is not Idris, though. It's a little bit more limited. I'm not quite as smart as Edwin Brady. Okay. Here, this is how the programmer creates their own custom types. So one type has a single field called x, and it has to always be between 0 and less than 4. It has to be 0 up to less than 4. Another type has two fields. The first one is 0 to less than 4, and the second one is 0 to less than 5. So one type can only have 4 possible values, with x of 0, 1, 2, 3. Another type can have 20 possible values. So hopefully that is clear enough to see why they're called product types. Any questions? Anything? Is that not clear?
How does it know x is an integer?
Because that's when the compiler compiles that less than or equal to, it restricts, it adds a constraint, additional constraint, that x is an integer and it's less than,
Okay.
So the compiler is smart enough to add that additional stuff in there. So then if we want to define both types, so it can be, so a value can be, if a value is an instance of both types, it can be either an instance of one type or an instance of another type. So that means there are 4 plus 20 possible values for both types, which, with no surprise, are called sum types. The combination of product and sum types gives you algebraic data types. And so you can build these things up, nest to any number of degrees, and everybody's happy. And all these things can be checked statically. But you do not have to put assertions onto these fields. They can be, you can leave them empty or unasserted, and they'll take any value. So that kind of gives the dynamic programmer a little comfortable place to sit if he doesn't want to take advantage of all the static typing goodness.
How would you read the last statement there, that both types come? Comp is that a built-in or something?
That's a good question. I've done this for like so long that these things are just natural to me, so I forget what I need to explain. The idea, like the core idea of Takada, is programming by composition. And so comp is a core library interface that all kinds of data types can implement. In this case, the compiler sees that comp in the expression of a def and knows that it has to be composing types. And so it does some type level compile time magic. But it uses the same form of comp as the library does, because the idea is that you're composing these two types. Does that make sense?
And does that define a function, or
Def does not define a function.
does?
It defines a value that's given a symbol. It defines, it assigns a value to a symbol that can be used later on.
So it assigns the composition of these two types, which is now like it can be either this or this.
Yep.
To this new label, both types.
Yep. And both
Which
types,
is not a type.
both types is a type.
Okay, but so the def type and def have different semantics, so you need both of them in the thing.
Yes. Def type is used to define a type that has fields.
Oh, I see.
And def, yeah. So, keep in mind this is to make it easy conceptually for people that are not used to static type programming, type level programming and stuff. And so, trying to kind of a little bit reuse some of the concepts that are familiar to them in a way that makes it easy for them to take advantage of these things. Okay, so algebraic data types. All right, we're in the home stretch. So here we have one type which has x, and another type which has x and y, and bogus type which has a, b, and c. So then this function, this is how you define a function with def in, inc the x field of R. So the dot x is a getter setter. If it has one parameter, it gets the x field out of that value R. If it has two parameters, it sets the x field of the of like R. Make sense? I kind of bungled that explanation. Okay, so that dot syntax comes straight from Clojure. So inc x field, the parameter R has a hidden assertion because of the use of these getters and setters. Every value passed into inc x field has to have an x field. Make sense? So that kind of that assertion, even though it's not stated explicitly, is just as real as any assertion that is stated explicitly. And it bubbles up, gets promoted up through the call tree, just like the others that we've seen. This is called row polymorphism, where it only says what field that value has to have. And it doesn't say anything about the other fields that value has to have. And so one type and another type would both be good types to pass into R, but bogus type would blow things up. And so the compiler can, possibly know that that's going to happen at compile time. And if it can't, it puts in a check at for at runtime. If you try to pass something in, it'll throw a runtime error and say you can't do this. So one of the interesting things about kind of where this stuff came from is Martin Odursky gave a talk at Strangeloop 10 years ago. I don't know, long time, called The Trouble with Types. And it really stuck with me. I mean, this is before I even started doing Takada. And he put up a type error on a slide, and it like filled the entire slide of this inscrutable error. And it's like, that's awful. Why? No wonder people don't want to do static typing if they have to debug their types, their type errors like that. And as I learned more about it, I realized that type level programming, where you're programming your types up, what you're really doing is a logic programming. And debugging logic programming sucks. I mean, it is just atrocious. But I do highly recommend the book, The Reason Schemer. It is a great book. I have a funny story to tell you about that I'll tell you later. But it's all about logic programming. And once you get like The Reason Schemer, stuff like Henley Milner makes a ton of sense. And then you realize why type errors are so awful. So in Takada, what happens is, let's say you have your call tree, and you have assertions that are down here at the leaves, and they bubble up. And two assertions conflict at a particular call site, where it says they try to assert two different things that are mutually exclusive. And the compiler sees that, and he says, the error he pops out is, you have a problem at this point in your source code. It gives you the file name and line number. And the assertions that are causing this problem come from this chain of calls. And so it gives you like a reverse stack trace of where the conflicts come from. If it happens at runtime, then it says, runtime, it crashes in the standard error. It says program crashed at this point, because that's where the assertion, or that's where the runtime check happened. But the assertion that caused this crash came from, it gives a list of file names and line numbers of the call sites where that assertion bubbled up from the leaf. So the idea being that you should reach for a debugger in Takada as a last resort. You should, the dream is when you're programming Takada, you're in the flow, an error pops up, you should know exactly what to do to fix that error. And you go fix it, and then keep going, rather than have to say, okay, crap, now play compiler, figure out what's going on, step through the code, yada, yada, yada. You guys know the routine. You should know by the error messages what the problem is. That's the ideal. And it should all be happening at compile time. That's also the ideal. Obviously, it's not going to happen, but okay.
I have a question
Yep.
about one type. Is that a polymorphic one type? Like, if I'm calling int x field somewhere on a one type where x is an integer, and I'm calling, concat string with space in another location on a different one type, is the compiler going to decide that those are mutually exclusive because they both rely on the same underlying type, or is it going to decide that this one type can have an int and this one type can have a string?
Man, you're good. Because so everything up to this point works. The dependent types, I need to add the less than, greater than for integers, but it works for string lengths, minimum string lengths. And so the integer check That's like really trivial. So everything else up to this point is concrete works stuff. I see a path to doing higher kind of types, which I think addresses kind of what if the x inside of one type is a particular type. Is that right? Okay. If not, then I misunderstood your question, and we can discuss it. But so higher kind of types. Everybody wants higher kind of types, it seems like. I think there's a path to implementing a constraint, an assertion, that will fit into this mechanism I've come up with that will give me higher kind of types. And so like if you map over a list, and you're mapping ink over a list, that means all of the elements of that list have to be an integer. I think I can put a constraint in there that will bubble up just like everything else, so that if you try to add a string to that kind of list, it'll throw an exception at that point, rather than when you're trying to map over it. So that's vaporware. It's in my head. And this idea for like error messages, I had that idea like 3 or 4 years ago, and just got it implemented. So I actually did it like late last year. So who knows when higher kind of types is going to come. But I think it's possible, and that'd be way cool. But then there's really, I mean, the only limit of what assertions can be in there are what we can come up with. Anything that can be asserted, I'm willing to take a crack at adding it to the compiler, so that we can drive out bugs from the runtime, move them into compile time, and stay in the flow, and do the happy things of creating great software. So that's the way the Takada type system works, and kind of the ideas and the dream of Takada. So that's the talk. Any questions, comments, whatever?
This is probably the clearest I've ever heard anybody explain some types and product types and algebraic data types. So that's really amazing. And also, 2016 ClojureCon had a Zork. Someone spoke about Zork. Maybe the implementation of Zork.
Yeah.
Closures.
I've been at every conch, so I was there. I don't remember that talk. Must have been a different one, but that I have to go back and look. So. And the way I explained those algebraic data types is not my idea. I read it in a blog post of somebody that I was like, oh, now it makes sense. So I just blatantly copied that blog post.
Especially with role polymorphism versus subtyping, like nobody explains that.
Well, I hope I explained it right,
Yeah.
because that's the way I understood it. And just like gradual typing, I could be wrong. And if I'm wrong, let me know, and I'll fix it, sort of. Okay.
Can you talk a bit about the pros and cons of outputting strings versus an AST or something for generating a secret?
Okay. This talk is going in a whole different direction. So the way Takada is built is the grammar is specified using a free applicative. And so it's actually just a data structure, the grammar. And that gets interpreted to produce a recursive descent parser. It could also get interpreted to produce an eBNF and spit out the eBNF of the grammar, which I've done, or do other kinds of things with the grammar. But if you spit out the recursive descent parser, then when that parses the source code, it spits out an AST, which is the data structure. It is the AST.
But is that a Takada AST?
It is. It's a Takada AST.
So why not go from Takada AST to a C AST rather than generating strings?
Because I'm not that smart.
Okay. Because I just wonder, anytime I see a string of source code, I wonder, well, can this name that you've chosen conflict with another name in the generated file? I don't know.
Yep, that's a problem. So when you compile a Takada program, one of the features is that you can pull in dependencies from any Git repo. So you can pull a file from any Git repo, like Go used to be able to do, except in Takada you can pin the SHAs, so you don't have the Go problem that they had. But you can pull the dependencies in, but no matter what you pull in, they all get pulled in as source and you only get one C file out. And Takada, the compiler, makes sure that none of the names conflict. But that's a problem because you can't do incremental recompilation, which I want to fix. So I want to talk to, because I frankly don't know how to produce a C AST.
Oh, I don't either.
Oh,
I've done it with
Dang
other
it.
languages. So if you want to have a JavaScript, well, either you can do what CoffeeScript initially did, which is just generate JavaScript code fragments and concat them, or you can just say use the SpiderMonkey AST or whatever, and then just use a standard to have that implemented in JavaScript.
so way back in the beginning of Takada, I wrote a closure program that cross-compiled the Takada program into LLVM IR. And it worked, and I had to write, low-level IR, which is just an assembly language, and that was something I'm familiar with, so it wasn't too hard. But debugging that stuff was a problem. And so I switched to emitting C strings so I could visually see what was being generated and debug it. The grand dream is to go back and do IR and address that problem.
But maybe it isn't a problem in practice.
It's not yet, but everything gets compiled to one C file, and the compiler has control over the naming of the C stuff, and so you get names like arg underscore, 10,211 kind of stuff, but it works and spits out pretty reasonable C that gets compiled and run, and everybody's happy.
You mean that only a single C file?
Only a single C file.
You anticipate that being problematic for
Yes.
Ledge?
Yep, I sure do. Whatever the rest of your question was, yep, it's going to be a problem.
What is control flow like?
So there are and or expressions that you can nest. And those are the only expressions that are lazy. So if you have an and expression, it evaluates the first expression. And if that returns a nothing, then it evaluates the next expression. And if that returns nothing, then it does the next. Until one of them returns a maybe, a maybe value with a value inside of it. And then the or is just the reverse. But that's the only place in Takada where there's laziness. And that's how you do control flow. Oh, yeah.
What's your approach to tail calls?
That's an interesting point. One of the things I'm most proud of, which only language geeks really get, Takada is reference counted. I'm an embedded programmer. I do not want GC pauses. I do not care how good the GC is. I do not want the pause. So, that's my quirk, whatever. But I also wanted tail call optimization and tail recursion. So for tail call optimization, I rely on the C compiler, the LLVM, to eliminate at the higher optimization levels, 02, 03 type thing. And I came up with the scheme for the reference counting that the compiler sees how many places a value is used, is going to be passed into other functions in a function, and it just increments the ref that number of times right at the top, or right where it's created. And so that means that the last call, the compiler has a chance to optimize that tail call away. For tail recursion, if you look at a generated function, it's just while one, the body of the function, and then if it actually returns a value, there's just a return in the middle of that while, which is crap if you're doing it as a human writing it, but the compiler doesn't care. And if it's a recursive tail call, it just goes around the loop again, rebinds the symbols and goes around the loop again. Thanks.
Does that reference counting scheme fix cyclical unreachability problem?
I think so. I think we're about out of time, but nobody showed up yet, so.
They're loitering outside.
Oh, they are? Well, then let's clear the room. Thank you guys very much. Appreciate it.